for the Center for Offshore Renewable Energy, Center for Offshore Renewable Energy, or C4. So this is actually the collaborative project between UMT and Petronas. We aim at developing an offshore hybrid renewable energy showcase powered by solar, wind, and wave energy. So for this Tech Talk under renewable energy team, it's my pleasure to introduce you to C4, which is now entering the third phase of the commissioning stage. Right, so this is the outline of my presentation today. I will start with a bit of motivation, and then I will introduce what is C4. And then I will move to the C4 system and key technologies. So for this particular topic, I will spend some time to show in more detail related to key technologies that we have at C4. Particularly related to wind turbines, floating solar, and so as the battery energy storage system. And then followed by challenge and lesson learned, and also future outlook and opportunities. And finally, I will wrap up with why C4 matters, especially in supporting Malaysia energy transition and sustainability goals. So globally, there is a strong momentum toward decarbonization driven by the framework like IMO's, which is, IMO's decarbonization target of 40% reduction by 2030. Also, globally, we know about UN SDG 7 related to affordable and clean energy. For the Malaysia, we have Malaysia commitment as well, which is Malaysia Renewable Energy Roadmap targets about 40% renewable energy capacity mix by 2035. We also have another policy related to energy transition, which is National Energy Transition Roadmap, which highlight offshore renewable energy as part of the renewable energy development in the future. So we see the gap, which is the marine sector has many untapped wind, wave, and solar potential, which is especially at the East Coast region. So this is where C4 comes in, which is a collaborative project between UMT and Petronas, aiming to pioneer an offshore hybrid renewable energy microgrid system that can sustainably power the islands, offshore platform, as well as remote coastal assets. So what is C4? Okay, so C4 stands for Center for Offshore Renewable Energy. Our vision is to establish Malaysia's first integrated offshore hybrid renewable energy system testbed, demonstrating technical viability and support future national deployment. So the development of C4 is made possible with the collaboration and support from our key collaborators. So we do have our collaborator is RIMA. RIMA Engineering contribute to solution for the offshore floating solar system. We do have support from Schneider Electric, which is in terms of switch gears and transformers, as well as the microgrid energy management system, which is Schneider has the product we call it as IPA system. And MyBest and Honeywell are the partners in terms of battery energy storage solution. So this is where our development begins with the proposed site plan at Pantai Tok Jembar. So this here is the Pantai Tok Jembar. We have a fisherman's jetty around here. So this is our proposed site location at the offshore. So here we have the area of about 120 meters by 120 meters area. So here we have our proposed site for wind turbines and also floating solar. And then also at the onshore, we have the site number 2 here, which is proposed for C4 station. So the area of this site is about 60 meters by 140 meters. So this is a Google Map view showing the coordinates of the wind turbines. And we have the offshore side and onshore side right here. So here we have 4 wind turbines and also one area of the floating solar platform right over here. And then here is the onshore. Okay, moving to our design based on the circuit diagram. So basically we have 4 wind turbines. 4 wind turbines feeders feeding to low voltage bus bar. So we have 4 wind turbines, 1 wind turbines platform dedicated for e-house, what we call it as e-house, which is the powerhouse lah, at the offshore. So 4 feeders to the low voltage bus, and then we have 1 feeder from floating solar. So this floating solar generation is about 220 kilowatt. For the wind turbine, we have 20 kilowatt each. Total about 80 kilowatt of the generation from the wind turbines now. So for the total generation from offshore, we have 80 kilowatt from wind turbines and 220 kilowatt from floating solar. So overall, we have about 300 kilowatt of power to be generated from offshore. And also at the offshore, we have some loads, especially the air conditioning system lah, to support the e-house, which is the offshore powerhouse from Schneider Electric. There are some loads in terms of aircon, lighting, as well as the low voltage equipment. And for this low voltage bus bar, we step up the voltage to 11 kV using the step up transformer to transfer the power to onshore. So we use submarine cable to transfer the power from offshore to onshore. So this is the SLD for the onshore side. So you see from here, we have the submarine cable coming from here, and the voltage is stepped down by the transformer again to 400 volt. So basically at the onshore, we do have some small generation, which is coming from building integrated photovoltaic, which is the rooftop solar parking. We have some 5 kilowatt here. And we do have some other feeders dedicated for battery energy storage system to store surplus of energy from offshore generation. But in this case, at C4, we have 3 different BESS from 3 different BESS vendors lah. The first BESS is the capacity about 426 kilowatt hour. Okay, and then the second BESS we have about 466 kilowatt hour, and the third BESS we have another 466 kilowatt hour. So we have 3 BESS feeding to the same bus bar lah, the low voltage bus bar. At the onshore also, we have some load facility. So in that load facility, we have some ice maker and also cold storage lah, to store the ice. Okay. So moving to C4 system and key technologies. Okay, so this is as you can see, this is the offshore side. We have 4 wind turbines. So here is the wind turbine platform number 1, and in this the yellow one is our e-house lah. E-house, we have RMU and transformer inside the e-house, and then from here we collect all the power from wind turbines, and the power from here will be delivered to onshore using the submarine cable. So basically, this platform design is a bit larger than other 3 platforms. So we use a submarine cable for each of the wind turbine to transfer power For example, from wind turbine platform 2, we have submarine cable to this to this is house. And then similarly for wind turbine platform number 3 and number 4, we do have some cables, submarine cable to transfer power to here. In the middle of the area, we have FPV, floating photovoltaic, with the area around 50 by 50 meters. Okay, so this FPV actually use the dynamic cable. So dynamic DC cable, about 56 core of 10 millimeter square of cables. So it's some part of the, half of the part of the cable is floating, and the rest leave it hanging under the sea. So this connection also have only one connection to our wind turbine number 1 platform lah. So that is overall overview, aerial view lah from offshore. And then here is our onshore station. So basically we cannot see from here. Actually, when we sit at this jetty, we can see the offshore platform, right? So at the onshore, we have our main building here. So basically in the main building, we have several room, office, and medium and low voltage room for transformer and RMU. And here is the building for load facility. Okay, and here is the rooftop solar, which is building integrated photovoltaic. And at the back of this main building, actually we have the area for battery energy storage. So we have 3 battery energy storage system here. I will show you that. I will show to you guys later that one. Okay, so I will move on to part by part of the key technologies that we have. Firstly, we have the wind turbines, 20 kilowatt each. We have 4 units of wind turbine from ELOS. ELOS is the maker from China. So for this particular wind turbine, it has the hub height of about 80 meters from the foundation. And the blades diameter is about 15.6 meter. And also there are some control panels. For each of the platform, we have wind turbines and also the control panel. So inside the control panel, we have the wind turbine controller, which is basically the rectifier. And then some bus bar, and also this is the inverter used for the wind turbines. So this is basically the foundation design of the wind turbines. We use the rectifier, and as you can see from the aerial view just now, basically we have the platform number 1 is larger than the other 3 platforms. So the size of the platform number 1 is about 6.6 by 10.5 meters lah. So because we want to place the e-house at this wind turbine number 1. And then the rest of the three platform, the size is about 6.6 meters by 6.6 meters, dedicated for wind turbine number 1, number 2, 3, and 4, right? Next is the floating photovoltaic or FPV. So we have a total generation from FPV is about, this is the DC side, which is 238 kilowatt peak DC side. So we have 3 inverters feeding the low voltage bus bar. Each of the panel size is about 710 watt. We have 14 panels in each string, and we do have about 24 strings in total, amounting the 238 kilowatt peak of DC side of the generation. At the AC side, we have 220 in total, which is 100 kilowatt inverter. We have 2 units of 100 kilowatt inverter and 1 unit of 20 kilowatt inverter with DC optimizer. So as you can see, this string dedicated for the one with optimizer lah. And the rest 22 strings with without optimizer, which is the output of AC of this 22 string is 2 unit of 100 kilowatt inverter. This one is 20 kilowatt. So from this panel, the DC power is transferred through this the dynamic cable, DC dynamic cable. We do have a DC protection box here at the floater and also at our platform lah. So, and then we have 3 inverters. So from these 3 inverter feeding the same bus bar, which is the 400 volt bus bar. And then the rest of the power will go to MSB inside the e-house. So basically this is the cable, the dynamic cable that is used to transfer the power from the PV panels to the platform. So basically we transfer DC current from the panels to the inverter, then inverter will invert the voltage to AC. Okay, so this is basically the design of the floaters from RINA Engineering. So for the floater, it has 24 rows and 14 columns to support a total of 336 PV panels. Each of the panels is around 710 watt. Okay. And then the configuration of the panel is set to be a 15-degree latitude, which is the angle if 15 degree is adequate to make sure that the surface of the solar PV panels facing the sunrise and until end of the day lah. And this is the illustration of the floater design by RINA Engineering. For the mooring lines and mooring system, it has about 36 points of mooring system. And also the HDPE structure outside the this pontoon of floating platform. Basically, there is a wave breaker made of HDPE pipe. HDPE pipe structure, the size is about 47 times 51 meters for wave breaker system lah. Alright, so this is about e-house, which is the offshore compact substation provided by Schneider Electric. So we have in this e-house, we step up the voltage using this transformer from 400 volt to 11 kV. And this is the transformer from Trihal, China maker lah, Trihal. And then RMU, this is the RMU, and then this is what is inside the e-house. So in the e-house, we have some air conditioning system lah to regulate the this e-house temperature. And then we have some other equipment such as the lightings and small power loads, as well as auxiliary load, wind turbine punya auxiliary loads. And at the offshore also, we do have the EPAS RTU panel, which is the instrumentation and control devices for EPAS system, which is our energy management system provided by Schneider Electric. So this is at the onshore powerhouse. Okay, so after we step up the offshore voltage to 11 kV, we transfer using the transmission is using the submarine cable, yellow one here. This is the submarine cable. Transfer the power to onshore. This is our powerhouse at onshore. So basically, we have the same equipment at the onshore, which is we have the step-down transformer from 11 kV to 400 volt. And then we have RMU. And this is MSB. Okay. So from MSB, it is distributed to the DBs, and we do have also the subswitch board for battery energy storage as well. Moving on, this is the control room at the onshore. So in our control room, we have the SCADA solution from Schneider Electric called ETAP IPAS. So you know, ETAP is software, right? It's software that we can use the logic. We can configure the logic for the operational philosophy. IPAS is the communication from onshore to offshore. So basically, for the IPAS system, as you can see here, is the architecture of the IPAS system for offshore side. Okay, so from offshore, we collect all the data from DPMs, okay, using TCP/IP communication, Modbus TCP/IP, and we have the point-to-point communication from this RTU panel to the breakers to collect the data as well as do the control of the circuit breakers at the offshore. So basically, this instrumentation is connected to the onshore by using the fiber optic. So we have the fiber optic. Actually, we use submarine cable. It's a composite cable. So apart from the power delivery in the composite cable, we also have the fiber optic. So we transfer the data from offshore using fiber optic to onshore, and then landed here at the server at the onshore. At the onshore also, we collect the data or control the instrumentation like breakers based on this RTU panel. Then there is a FO ring here to communicate from this server, the IPAS server here, with the onshore servers. So basically, this is IPAS server with the ETAP hybrid PPC. Hybrid PPC is the controller that we can configure how much for example, how much generation we want to set for the offshore generation to charge the battery, for example. So this can be done by the ETAP software. So we have some computers for HMI purpose, so for control and monitoring purpose at our control room. So we have 2 computers here. And at the onshore also, we have a location for battery energy storage. As you can see here, we have 3 different vendors, battery energy storage from 3 different vendors. The first one from MyBest or Genetech Technology from Bangina. So this one served as our grid forming, which is this battery energy storage will provide frequency and voltage reference to the rest of the inverter-based system, meaning that this is the key technology to replace the MB because this is the off-grid system. Of course, we need to control the voltage and frequency at 400 volt, and also the frequency should be within the 50 hertz for the inverter to synchronize with the grid. So we have Sita Global MyBest as the main battery energy storage as a grid former as well, and we do have some other backup of the battery storage from Narada Technology, provided by Honeywell, and also from PRCB as well, Petronas Resources Berhad. They provide Sopro Energy battery energy storage. So it has different capacity. For example, for this one is 4 to 6 kilowatt hour with different cooling technique. This one use air conditioning cooling for the battery storage. But for the other 2 battery storage from Narada and Supro, they use the liquid cooling method, which is much more stable in terms of power consumption. All right, so for this 3 battery energy storage, it is connected to the common bus bar, which is we have here is a sub-switch board. Okay, sub-switch board SSB for the battery energy storage. So So this is the battery energy storage area. We have MyBest, Narada, and also this one is Supro. Sorry, this one is Narada and this one is Supro Energy. So from this bus, there is a feeder, 3 feeders to SSB subswitch board. This one, okay, and then directly connected to the MSB at the powerhouse. And other than FPV and generation from wind turbines, we do have alternative generation from wave, which is we have a patented wave energy converter by Prof. Zamri, our VC. So this is the 10 kilowatt system, which has been developed by UMT. And we are going to attach this wave energy generator to this on this jetty. This is the jetty dedicated for this wave energy converter. And for this wave energy converter, actually, it is not integrated with the power system that we have here, but it works as a standalone system. So, but in terms of data collection, actually we have the communication interface, and we have the communication and collect the data from of the operation of this wave energy generator later on. Maybe some of you ask why this wave energy generator we didn't connect to the grid, because the inverter of this wave energy converter is quite old. We have a single phase inverter, so we cannot connect it to our 3-phase system. So basically, it will provide power to the local load or standalone loads. But still, the generation from this wave energy generator, we can monitor and log the data of the generation from this wave energy converter. And to support as a backup for the onshore, we do have some small amount of rooftop solar parking, rooftop solar for backup, which is around 5 kilowatt. So this is basically our rooftop solar park. Okay. And part of the generation will be supplied to our onshore load, mainly on the air conditioning system lah, banyak ke arah air conditioning system, and also part of our CSR basically we provide the cold storage and also the ice maker as part of what we call as our CSR to provide the ice from the generation from our system to local fishermen. Okay, so this is what we have done after our first power that day. We managed to produce some ice lah, yeah. So this is the ice maker. All right, so moving to challenge and lesson learned. Okay, since this system is the nearshore and offshore, of course, we have some corrosion problem in terms of material. Most of our equipment, we have we don't use the stainless steel. Some of them use galvanized. So it is when it's exposed to the salty environment, some of the equipment cause corrosion. For example, submiss intrusion causing our bus bar to oxidize, and then it triggers. This bus bar refers to one of the battery energy storage PCS bus bar. So it triggers alarm because of the oxidation of the bus bar. And then PCB board reliability issues, which is we found that some of the PCBs got problem because of the exposure to high humidity and also salt exposure. And then secondly, when the battery energy storage arrive, because it comes with 50% of the state of charge capacity, we need to charge it first. So to charge it, we need to operate it in on-grid mode. So basically, we found that our TNB grid to charge the battery, TNB grid is not stable here, which is sometimes the voltage drop to, for example, 360 volt, causing the battery energy storage PCS fail to synchronize lah. So when the voltage drop or unstable, we cannot operate on grid mode and we cannot charge our battery. Similarly to the genset, we order some genset from nearby provider, from Terengganu. Then we found that actually for the genset, to charge the battery, we need a genset with controllable frequency and voltage, because when we use genset which is not stable in terms of voltage and frequency, it will cause the battery energy storage PCS cannot synchronize and trigger some alarms. So these are the two things that we find out during our initial start operation, which is when it comes to instability of the grid voltage, the synchronization of the battery energy storage PCS will not be done properly. And we found that some of the design of the battery energy storage PCS, they comes with unprotected events, which is when we see inside the event, they didn't come with the submit filters, which is it is exposed to submit, which is end up with the corrosion to the event system. And also for the wind turbine, okay, this is our experience from commissioning of the wind turbines, which is last time we ordered the wind turbine without the dump loads, because we consider that since we have the battery energy storage, why not the generation of from the wind turbine, we directly store it in our energy storage. But basically, when we start operation or commissioning of the wind turbines, we found that it is compulsory to have the dump load, because in our scenario here at Eastern region, or maybe Terengganu, we experience a lot of wind gust situation. For example, if wind gust change the speed, if wind speed change, let's say during wind gust from 5 meter per second to suddenly to 25 meter per second, it will the generator will generate more power, which is causing the voltage rise. So when it comes to voltage rise, the power cannot go anywhere. So we cannot divert the power, and causing the wind turbine blades to spin faster. Then it affect to the protection system of the wind turbine itself, which is some of our experience during wind gust, during commissioning of wind turbine, and subjected to wind gust, it caused some of the capacitor to burn out, and failure of the some bolt has been loosened, especially the mechanical part got stressed at the pitch angle adjustment system. So we retrofit it by using the welding. So there are the things that, so now we are ordering the dump load, and we will installing the dump load at 4 units of our wind turbine. So basically, this is something that we have learned. Number 4 is about the transformer energization and inrush current. Okay, at the beginning of the commissioning stage, we need to energize the transformer. So this transformer is a 500 kVA transformer, which is we have the battery energy storage from MJB to energize this transformer. This transformer, that battery energy storage capacity, actually that inside the battery energy storage from MJB, they have the isolation transformer, which is half of the size of our transformer. So during energization, we fail the system trip during energization of the transformer. The system trip for multiple times. So we need to revise our switching procedure and look back what is the cause of the trip, and then we found that we need to revise the switching procedure to energize not only one transformer, but energize the first transformer with the power cable, submarine cable, and then switch off, and then switch off for 30 to 1 hour, 30 minutes to 1 hour, and then switch on again, energizing the second transformer at the offshore. So something that is quite complicated because in our system, basically we have onshore and offshore part, which is separated by 11 kV transmission system. So I'm mentioning here it's complicated because of in our system, it is a microgrid system that not only comprised of transmission but also distribution. So combined all together becomes a off-grid microgrid system lah. So that's why this part of this one is quite challenging. We spend some few days lah to settle this. Okay, number five is battery energy storage breaker tripping during solar output. This one, sorry, I got a phone call. Okay, number 5 is battery energy storage system breaker tripping during high solar output. Okay, this one we experienced during when the state of charge nearly full, which is for example during sunny days, our FPV, floating photovoltaic system, can generate the power out of 220 kilowatt. It can generate up to 170 kilowatt, which is quite high power for charging the battery energy storage. So when the battery energy storage state of charge nearly full, which is nearly 100%, it will trigger the circuit breaker. So circuit breaker will trip because of a high amount of power charging the battery energy at that time. So that's the case where we need to set the standard operation procedure for battery charging. So in this commissioning stage, we try to make sure that when the state of charge nearly 90% or 95%, we put our operator, we make sure that our operator to keep their eye on the charging, which is they will control the solar PV capacity to reduce the capacity, so to make sure it can slowly charge our BESS at that time. So basically, we're still in the process of fine-tuning the ETAP, IPAS, or our SCADA system, meaning that we are doing manually lah in terms of control and optimization of our control philosophy. So these are some of the photos to share with you guys, something related to the corrosion of our system. As you can see, we need to this one, this toggle, it's broken just in few months. Broken because of the salty condition or salty environment. So we put the something like this, the housing for this toggle, and you see some corrosion. This one, our best PCS, see some corrosion here because of the submist. So this one that I mentioned, that the bus bar trigger alarms because of the poor contacts of the bus bar sensors. So because of this corrosion, bus bar oxidize, and then it triggers alarm, causing our BESS system to shut down. Okay, and then there are some also there are some good things about from battery energy storage vendors. Some vendors, they put the submist filter for their PCS. So submist filter will isolate, will make sure that no intrusion of the submiss are inside the system. So this one is a good example. And there's another best system which is no submiss filter. So for example, this one it is exposed to the corrosion. Okay, future outlook and opportunities for this C4 project. Basically, it is something scalable. This is a showcase. We will do more experiment on that. And then in the future, of course, it is scalable and adaptable for deployment for larger scale. For example, we can do the same thing at the offshore oil or gas platform, remote coastal islands, maritime infrastructure, and so on. And then for the battery energy storage, we do have for battery energy storage part and also renewable energy feeders, we do have some spare breakers if we want to expand our generation or storage capacities later on. And then this project is actually other than collaboration with Petronas, also we collaborate with Instep for talent development. And then for our wave energy converter, basically it has been patented, and then waiting for installation, and we will monitor the performance, and hopefully this WEC can be commercialized. And then we hope that our Center for Offshore Renewable Energy at UMT here will contribute to our national energy goals in terms of, for example, the policy, our government policies like National Energy Transition Roadmap and also Malaysia Renewable Energy Roadmap. And last but not least, why C4 matters. Okay, so of course, this project aims to contribute also to our national policy in terms of renewable energy, also energy transition. And secondly, big lab research with real world deployment. So this test rig actually this we can consider as microgrid test bed. And of course, it can be expandable and deployable in a larger scale system. And also we hope that with this project, it can strengthen Malaysia offshore renewable energy capabilities regionally. And this is also one of the things that proven a collaborative success between academia and industry. We have this collaboration with Petronas now, and we hope for future collaboration with other partners as well in the future. Okay, I think that's all from my presentation. I give back to the NC.
Okay, thank you very much, Dr. Zalani. So very informative and insightful to the audience, of course. So without further ado, let's go to the Q&A session. Mr. Ahmad Nazri. Yeah, please proceed with the
Dan, Dr. Sai, Don. Saya mewakili sikit lah on behalf of C4 team. I think in addition to this, maybe kena ada caveat preemptor sikit lah. Dia lesson learn apa semua tu still ongoing lah actually as of now, especially on yang mana related to marine, TNI and so on. Kita still compiling and have yet to go through the final list together with the kita punya partners lah, yang contractor yang buat TNI, contractor and so on. So few things yang mungkin lepas ni kita akan make it official later on lah. Itu satu. Lepas tu yang maybe another thing on future punya kita punya maybe innovation and coming forward with future ideas on ecotourism. Saya tak pasti Dr. Zalani ada mention ke tak ni, macam tak nampak sangat.
Betul.
So ecotourism actually
InsyaAllah.
Saya punya komen satu doktor saya dah bagi tahu kok, Dr. Hairi, Dr. Assam minggu depan lah masa Presiden visit tu. Yang jetty tu mungkin kita boleh improvise to allocate dekat tepi ataupun kat belah yang ni untuk future kalau ada visitor coming in and so on. maybe kita boleh invest on getting our own boat untuk bawa personnel, visitor ke apa semua. So sebagai salah satu cara untuk generate income lah. Itu maybe something yang kita boleh work on between UMT dengan Petronas nanti lah. Kan itu. Lepas tu yang lain-lain mungkin ada komen daripada ada tim kita yang sekarang ni, Syaz dengan Dr. Harry pada sekali dengan saya. Mungkin ada on certain things yang kita akan further refine before we presented to all the audience later on lah nanti. Itu sajalah setakat ni. Saya punya opinion maybe ni sikit sebab saya part of the team. Kalau ada yang lain nak tanya kan sila-sila. Thank you.
Okay, thank you, Ray. Okay, we are running out of time, so perhaps I can only allow another one question from the audience. So, is there any? Okay. If not now, perhaps you can type in the chat box as well, and perhaps after this, Dr. Zalani can answer as well from the chat if there is any further question after this. So, thank you very much, Dr. Zalani, for your insightful sharing on this IPO project.
Yes, if anyone have question can directly contact me or Dr. Hairil or Dr. Asabuddin and also our Petronas team as well.
Okay, thank you again. Okay, so next let's move into our second speaker. With the title of Optimizing Rotor Shape for Better Energy Performance by Dr. Cheng Yi Ng. Allow me to briefly share about Dr. Ng's background. Dr. Cheng Yi Ng is a senior lecturer in Department of Civil and Environmental Engineering at University Technology Petronas, UTP. With over 10 years of experience in offshore engineering, her research focuses on marine renewable energy, including hydrokinetic turbine, floating multi-energy platform, and wave structure interaction. She has led several national and international research projects and published extensively on ocean energy system. Dr. Ng currently serves as technical committee for the ASME Offshore Mechanic and Arctic Engineering Conference and Offshore Technology Conference Asia, OTCA. Her work bridges academic research with industry application to support the development of sustainable marine infrastructure. So without further ado, I would like to hand over to Dr. Ng to deliver her talk. Over to you, Dr. Ng.
Thank you, IR Azlan. You can see me, you can hear me, you can see my slide.
Yeah, I can see you.
All right, that's good. Okay,
That's
so thank you so much for having me today. And like IR Azlan introduced, so my name is Cheng Yi, or you can call me Carol. So I'm from University Technology Petronas UTP, where I teach, I do research in offshore engineering and also focuses on offshore renewable energy. And I also coordinate an MSc program that we call it as a MSc in offshore engineering. So if you're interested, do drop me an email about that. And I'm also heading a smart infrastructure modeling and monitoring research center. So a lot of what we're going to discuss today will be overlapping with what my daily work is about, what I teach, and what I'm working with. So this work is basically a work by my undergraduate students, Novi, and for her final year project with the title of Numerical Investigation of Rotor Aspect Ratio Effect on an Augmented Drag-Based Hydrokinetic Turbine. Or in a simpler manner, it means that we are looking at the optimization of rotor ratio for a better energy performance. So I would like to take this opportunity also to thank my co-authors, Xiang Ying from UTP and Mok Chen from University of Stavanger from Norway. And before I start, let me just give a little bit of context setting. So today, over 55% of the world population is living in under or in the urban area, and by 2050, the number is expected to increase by about 70%, according to UN. So this rapid urbanization has caused with a sharp increase in energy demand. So not just for a big city, but especially in the coastal and developing regions where infrastructure is often fragile and also outdated. So adding to the climate pressure and also rising of seawater levels, a strong storm and also frequent flooding, all these problems, right? So coastal city in particular is actually caught in a double problems. So that is why we need more energy to support the growth of these cities, and also they will need more exposure to the climate risk. So that is why we need to focus more on this the coastal cities. So now, what do we do, or where do we look for energy that is clean, reliable, and right next to the place? So one of the answer is actually the ocean. Ocean, basically, we all know that it's covering 70% of the planet's surface, and it upholds an untapped energy potential. So where we have a wave, we have tide, we have ocean current. So all these are basically steady and natural flows that we can harness. So a little bit if you compare with solar and wind, which is intermittent, so ocean energy is more like a tidal and current is highly predictable. So that makes it extremely valuable, especially in terms of balancing the energy mix and also stabilizing the supplies. And most importantly is that ocean energy can be produced close to where it is needed. Like mentioned just now, it's more towards the coastal city. So that will be reducing the transmission losses and enabling the more decentralized, resilient, and energy system for coastal cities. Now, when we talk about ocean energy, we are talking about energy that is coming from the natural movements and also thermal properties of seawater. So that will include wave, tides, ocean current, and even for temperature gradients from the ocean surface and also deep water. So each of these resources have behaved differently. So for example, wave are wind-driven and variables, and tidals are lunar-driven and highly predictable. Ocean current offer a steady flow in terms of certain regions. So these are some of the different behavior of the ocean energy that we can look at. So have a quick look of the scale, what is available to us. Wave energy alone, globally, we are talking about 2,500 terawatt hours per year. And then OTEC, ocean thermal energy conversion, we are talking about 10,000 terawatt per year. Tidal energy, yes, although it's small, it's about 1,200 terawatt per year. So across all these resources, we are talking about tens of thousands terawatt hour per year of renewable, local, and largely untapped energy. So that is why we are bringing into the focus here that ocean energy is actually a huge potential for us to tap in. Now, particularly for this project, we are looking at ocean current, right? So why are we focusing in ocean current? So ocean current energy is directly supporting the three pillars of the global energy trilemma. So we are talking about energy security, equity, and also environmental sustainability. Ocean current are steady, and it is continuous, predictable, and it offers a reliable baseload energy. So that is why it is actually ticking one of the boxes for this energy trilemma. And this system can actually deploy near shore, and it brings the clean energy to island or coastal community, like we mentioned just now. That is additionally, this technology is actually modular and scalable, so very well suitable for decentralized and community level power access. So they are basically fully renewable and zero emission at the point of generation. So since the system are submerged, so visually they are not bringing any impact. So this will make them compatible to any of the marine protected zone. So in short, ocean currents are one of the few resources that tick all the three boxes of this energy trilemma. So now, if we look at how we can tap into the ocean current energy or the technology, so we are looking at hydrokinetic turbine. So this device is generate the electricity directly from the natural movements of the water. So no dam is required, no reservoir is required, which minimizes the disruptions to the marine environment. And if you look at this, so we can see that hydrokinetic turbine can be categorized as axial flow and also the cross flow. So in our study, we focuses on the Savonius turbine, which is one type of the cross-flow turbine that we will be working on. So among many of these, the reason that we select Savonius is because of the simplicity. So it works in a drag force, so it doesn't need an alignment to the flow. So it can actually have a self-start, even though it is a very low velocity. And that makes it a very attractive for an off-grid area, so where maintenance and control system are limited. And it is also low cost because it's very simple in terms of the design, right? So it is low cost, it's scalable, and it is very easy to be fabricated. So however, yes, the efficient, there's always a balance, right? When you close the door, so it will open another door for you. So here, the efficiency of Savonius turbine is low. So what is our ultimate goal is that how can we improve the performance of that? So in previous study, we have done a few of the parametric study, and we have looked at a few of the strategy in terms of optimization. So we have looked at different types of the blade shape in terms of the blade number, and we introduced end blades, diffuser, and deflector. And in this current study, we are looking at the aspect ratio. So if we look at aspect ratio, what does it mean by aspect ratio? So aspect ratio is actually the ratio of rotor height to the rotor diameter. So it is actually a key parameter that is affecting the swap area and also the flow behavior and also the structural design. So we have structured the simulations into two configurations. Case number one is that we fixed the rotor height and we varied the diameter. So this will let us observe how increasing the swap area will be affecting the torque generation and also efficiency. And the second case they were looking at here is that we fixed the diameter and we varied the height. So this isolates the effects of vertical blade extension and to see how much we can gain from stretching the rotor upward at a constant width. Now, this will be the flow of the methodology that we have conducted. We used a CFD method, and what we've done is that we have constructed the 3D CAD model of the Savonius turbine. Then we bring that into the CFD model, and we have used the solver, considering the URANS framework and also K omega as a turbulence model. And we validate that. So before running the actual study, so we have conducted the 3 validations. So we have conducted the mesh conversions and then the domain size testing, as well as the time step analysis to ensure that everything is okay before we go into the parametric study. So once it's validated, then we have our core work, which is focusing on the rotor aspect. That is ranging from 0.5 to 1.5, and for both the cases that I mentioned just now. So by considering the different cases, it allows us to actually isolate the different effects of the rotor proportional to the turbine in terms of the torque and also the efficiency. So that is also that we are looking at in terms of the augmentations of that. So all this will be, we can get the effects measured quantitatively from the CFD outcome. So this is how the turbine looks like. And then all the parameters are included in this table. So if you'd like to know more, and then you can go to, the paper will be published soon. So you can get it online maybe in 1 or 2 months later. And basically we are looking at only a rotor diameter of 1 meter. So that is the benchmark that we're looking at. And then with the width of 1.23. So all the major parameters like mentioned, so it is here. So you can have a look at that. So before we run that, so we make sure that this is the results of our validation study, like I mentioned. So we have conducted the mesh convergence and the domain size study and also the time steps. So based on this, we can see that by considering the refinement level 6, with the 3.3 million cells, it actually gives us a very minimal deviations compared in terms of the torque value. So what we have done is that the next thing that we look at is in terms of the domain size. So we also ensure that the deviations is actually in a range of not more than, in a range of plus minus 6%. So because some study has shown that the deviations, if you look at, for example, the torque, if you compare with the reference torque, if it is within that range, so it is considered it's acceptable. So you can actually proceed for it's validated in a way, yeah. Okay, so this is after the validation. So we explore how the rotor aspect affecting the torque generation. So this is for case number 1, where the rotor height is fixed and we vary the diameter. And we found that when you have a lower aspect ratio, right, so it's actually producing a higher peak torque and at the lower tip speed ratio. So this is because we found that when you have a larger swept area, so it generates a stronger initial drag force. So this is actually good to which helps in terms of the startup performance. And on the other hand, that we can see that when you have a higher aspect ratio produced, lower torque the overall, but the peak later is remain more stable over the tip speed ratio range. So in here, we can draw conclusions that the best torque performance appear to be at the intermediate aspect ratio, ranging between 0.75 and also 0.85. At 0.875, where we see that there is a balance between the performance over the wide range of the T-speed ratio. And then we are looking at the second case here, where we fix the rotor diameter and we vary the height. So we observe here that all the aspect ratio torque increases with the T-speed ratio. You can see a standard trend here, yeah. So the trend shows that the torque increase with the T-speed ratio and then it peaks and then it drops. So we can see a consistent trend here. So comparatively for all these cases, we can see the aspect ratio of 1.23 performed the best, and it delivered actually the highest peak torque value, and then it maintained at the performance across the operating range. And then we have shift from the torque into the efficiency. So we are measuring in terms of the power efficiency, power coefficient, the CP. So both case 1 and case 2, we can see that there is actually a consistent pattern where we see that the CP is actually increasing with the T-speed ratio and peak, then it falls down. So the best performance lies in the also again that is at the intermediate aspect ratio between aspect ratio 1 and also 1.23, which achieved the highest CP value at with that of 0.5 at the aspect ratio of 1. And then the next thing that we look at is in terms of the torque coefficient. So this torque coefficient basically helps us to understand how efficient is the turbine convert the flow into the torque. So peak torque CT value that we observe here is 0.652. That is achieved when it is at the aspect ratio of 1 at the T-speed ratio of 0.75. So here we see that again that intermediate aspect ratio between 0.8 and 1.23 is actually showing a consistent and stable CT trend, so making them attractive for if you want to have a deployment or real world situation. So this will be something that we can look at. And then when we have a high aspect ratio like 1.5, right, it actually shows a moderate CT performance, but with the noticeable decline at the high T-speed ratio. So this is causing a flow separation, so which is actually dragging down the performance of that. So that is why the best performance that we look at, we can observe here is still within the intermediate aspect ratio. So a little bit of a key takeaway from this study. So we found that rotor diameter influences the performance more than the rotor height. So that's the first thing that we look at. And then among the tested case, the best performing aspect ratio is 1.0 for case number 1, whereby we can achieve the highest CP value of 0.5 at the T-speed ratio of 1. And then why is that happening is because basically when you have the aspect ratio of 1, so it actually gives a good balance. So it can avoid extra drag force, and then it deliver a strong and stable torque. So this is this could be assuming as the best performing for both the energy capture and also the structural stability. All right, so that basically brings me end of my presentation. So thank you so much again for having me. And I have a QR code here. So if you'd like to reach out, so do drop me an email here. I have my email as well. So feel free to talk to. So I hand it back to the session chair here. IR Azlan, pass it back to you.
Okay, thank you very much, Dr. Carol. So let's open to the floor if there is any question. Any question, you can just open your mic and straight away ask the question. Okay. If there is no question, we can proceed with the next agenda. But before that, if there is any question after this, we can straight away contact Dr. Carol as per QR code mentioned or shown just now for further clarification. So with that, we'd like to thanks Dr. Carol for your sharing today, very insightful as well. And before we go next, before I share the QR code, let's take some picture together. Appreciate if all of us can open your camera for me to take picture. Okay. One moment. Okay, I can smile. 1, 2, 3. Okay, one more. 1, 2, 3. Okay. So now I will show you the QR code for attendance purposes. One moment. Okay. Hope you can see the QR code. I will put it in the chat as well. Okay, that's all. Okay, with that, thanks again to Dr. Zalani and Dr. Carol for becoming our speakers today. And I would like to thanks as well all the audience who joined our session today. So we welcome you to join as well our future Tech Talk. And if there is, we will announce again and we will share it as well for that session. So we have come to the end of our session today. Thank you again and bye. See you in next Tech Talk. Assalamualaikum warahmatullahi wabarakatuh.